Hello viewers, you are welcome to this video. Today I want to introduce you to Lagrange Polynomial Interpolation. Lagrange Polynomial Interpolation. First of all, what is polynomial interpolation? Polynomial interpolation is a method of estimating values between known data points. Again, polynomial interpolation is a method of estimating values between known data points. Now, Lagrange interpolation can be used to obtain an exact fit to a set of data points. What this means is that, let's assume that I've been given a table like this. These are S values. Let's say 1, 2, 3. These are the S values and these are the corresponding functional values. So, let me say 2.5, so 7.6, 10.4. Now, you can give me something like this and ask you to come out with a function. After getting the function, then you can ask you to find, say, f of 1.3. What is the functional value of 1.3? So you need to first of all get the function before you can get functional value of 1.3. You see, that's why we are saying that the Lagrange interpolation can be used to obtain an exact fit to a set of data points. So the exact fit here means that you can get a suitable polynomial to describe a given set of data points. Okay, now let's consider constructing a linear polynomial to pass through these points x0, y0, and x1, y1. Now, because it's a linear polynomial, we expect it to be like this. P1 of x is equal to a0 plus a1x. Because it is linear. This is a constant term, and then this is a1x. So you see that the highest power of x is 1. That is why it's a linear polynomial. When the highest power of x is 2, it is quadratic. If it is 3, it is cubic, and so on and so forth. So you can say if p1 of x is this, then a0 plus a1. Now x is s0, isn't it? If you are looking at this point, x is s0, so we have s0, and this should be equal to the corresponding y value, y0. This is equation number 1. Similarly, if you're going to use this point, you are going to have a0 plus a1 x1. I say because this is the x coordinate and this is the y coordinate, and this is equal to y1. Equation number 2. Now, viewers, if you decide to solve these two equations simultaneously to obtain the values of a0 and a1, you can do something like this. You can say equation number 2 minus equation number 1 implies, if you subtract equation 1 from equation 2, you are going to have a0 minus a0, it will go to 0. So you are going to have a1x1 minus a1x0 is equal to y1 minus y0. Don't forget these are subscripts. Now, this implies that a1 can come out as a common factor, x1 minus s0 is equal to y1 minus y0. Isn't it? That is this way. So this implies that a1 is equal to y1 minus y0 all over x1 minus s0. You have been able to make a1 the subject from here. Okay. Now, having obtained this, we can substitute this one into equation number 1 to get the corresponding expression for a0. Okay. So, you can say substituting a1 equal to y1 minus y0 all over x1 minus x0 into equation 1. Don't forget to circle your equations. Gives so wherever we see a1 here in equation 1, we are going to put this one. We are going to put y1 minus y0 over x1 minus x0. So it's going to be like, it's going to be a0 plus, I've seen a1. So I'm going to write y1 minus y0 over x1 minus s0 times x0. This is equal to y0. Now we are going to solve for a0. We want to make a0 the subject. So this will straight away become a0 is equal to y0 minus the whole of this will go to the other side. So let's expand it before taking to the other side. So we're going to have s0 y1 minus s0 y0. Are you seeing it? All over x1 minus s0. Now don't forget y0 is the same as y0 over 1. So let's find the LCM here. If you find the LCM, you are going to have x1 minus s0. Isn't it? Now, x1 minus s0 divided by 1, you are going to get this one. So x1 minus s0 times this. You are going to, so this one will be x1 minus s0 all times y0 minus x1 minus s0 comes into x1 minus s0 1. So if it is 1, then you are going to get what is at the top. So s0 y1, and then don't forget here is negative 1. So negative 1 times negative 1 positive. So plus s0 y0. So this is a0. Now, this means that a0 is equal to, let's expand this one. If you expand it, you're going to get s1 y0 minus s0 y0 minus s0 y1 plus s0 y0 all over s1 minus s0. Isn't it? Now let's see if we can do some cancellations. Negative s0 y0 is here, and you have positive s0 y0. So this will cancel this. So if you do that, I'm going to have x1 y0 minus s0 y1, because this is going to cancel it. All over x1 minus s0. Isn't it? Now this one is the same as, I want to write it so that it will look like this one. If you look at the a1, y1 comes first and then followed by y0. So I'm going to let y1 come first here. So this one is the same as s0 y1 minus x1 y0 all over. You see that I have interchanged the positions of this and this, so I can do the same down here. S0 minus x1. Yes, this is true. Yes, the explanation is this one. You have say 4 minus 2 all over say 2 minus 1. What this means is that, what I've done, what it means is that this is the same as 2 minus 4 all over 1 minus 2. Let's check it. 4 minus 2 is 2, divided by 2 minus 1 is 1. So that will be 2 divided by 1, and that is 2. Now let's go to the right hand side and see 1. Again, 2 divided by negative 1 is 2. So it means that this is true. We are going to substitute these values, a1 and then a0, into the linear polynomial and to see what will happen. We want to see what will happen when you substitute a0 and then a1 into this polynomial, linear polynomial. Okay, so let's do that. So let me clean this side. These are the expressions. You need this and that. So I can clean this side. This is a0, don't forget. So if you do that, so you can say substituting. So you can say substituting substituting a naught equal to s naught y1 minus s1 y naught over s naught minus s1 and a1 which is equal to y1 minus y naught all over s1 minus s naught into p1 of x is equal to a naught plus a1 x. We have so that means yes, I'm putting this side. So we have the polynomial is going to be p1 of x is equal to now a naught is the whole of this s naught y1 minus x1 y naught all over s naught minus s1, isn't it? Plus a1 times x. A1 is this. So y1 minus y naught all over s1 minus s naught times everything times x, isn't it? Now, this is the same as, let's continue from here. This is the same as p1 of x is equal to s naught y1 minus x1 y naught all over s naught minus x1 plus, let's expand this. So this one will be x y1 minus x y naught all over x1 minus s naught. Isn't now let's find the LCM. If you find the LCM, you're going to have x naught minus x1 times x1 minus s naught. Isn't it? S naught minus x1 comes into the whole of this. To cancel this, we are going to have x1 minus s naught. So we are going to have x1 minus s naught times what is at the top? S naught y1 minus s1 y naught. Isn't it? Now x1 minus s naught comes into the whole of this. To cancel this one, so you'll be left with s naught minus x1. So plus s naught minus x1 all times xy1 minus xy naught. Isn't it? So you have it this way. Now at this point, you look on the board. At this point, you see this one is same as s1 minus s naught times s naught y1 minus s1 y naught. Isn't it? Now I'm going to write this one so that s naught minus s1 so that it will look like s1 minus s naught. And to do this, I can simply say minus of x1 minus s naught times whatever is here. Let me explain this one. You see, this from here to here is the same as this. Now let's try to expand this. This one will be negative 1 times x1. That is negative x1, which is the same as what was at the top here. Now negative 1 times negative s naught. Negative times negative is positive, so this one will be s naught. So this from here to here is the same as this, isn't it? And we are doing this so that this will look like this, it will be the same as this, it will look like this. And then if you are able to get that, you can factorize that one out, you can bring it out, isn't it? So mathematics, when you are doing, you have to be smart. So you can now see that s1 minus s naught is a common factor to these two. It's a common factor. So it means that you can bring x1 minus s naught out. When you do that, then you are going to be left with s naught y1 minus s1 y naught. Isn't it? This one has been brought out. Minus sy1 minus sy naught all over s naught minus s1 times s1 minus s naught. Isn't it? Now, the whole of this is p1 of x. P1 of x. Now, let's look on the board. You can see that S1 minus S0 is here, and you have S1 minus S0 also being here. So this will cancel this. Isn't it? So if you do that, then you are going to be left with what you have here. So let's expand it. This has cancelled this. You are going to have S0 Y1. Let me write it well. S0 Y1 minus S1 Y0. Isn't it? Minus, let's expand this, sy1 negative 1 times negative sy0. So this one will be positive. Negative times negative is positive. So sy0 positive. All over. You see, this one has cancelled this. So we left it s0 minus s1. Isn't it? Right, yes. Now, let's continue from here. Continue this. You want to derive something, you want to come up with something. That's why we're going through all this. And it's not difficult at all. This is not difficult. Now, let's try to group the like terms. This is y1, y0, y1, y0. The y0 should go to one side and the y1 should go to one side. So let's start with the y0. So you're going to have p1 of x is equal to xy0. Let's begin with the positive. sy0 minus x1 y0. Are you seeing it? Now we are done with the y0. Let's move on to the y1. Let's move in the positive plus, yes, s0 y1 minus xy1 all over s0 minus s1. Now, this is a common factor to these two. So it means that you can write this as s minus x1, and the common factor will come out. And then when you come here, y1 is a common factor to these two. So you have s0 minus x, y1, all over s0 minus x1. This is p1 of x. Now p1 of x is now equal to, now you guys only have something like this. When you have a plus b all over c is same as a over c plus b over c. So similarly, we are going to write this one as, this is the same as s minus x1 minus all over s0 minus x1 plus, then I'll go to this side, s0 minus x1 x, s0 minus x all over s0 minus x1. Isn't it? So I can put this in back. I can do this. Let me do this one this way. This way, and then y1. Isn't it? Now, this is equal to, you see that this one is x minus x1. And this x minus x1 all over s0 minus x1 y0. You see, this one has begun with x. So let's move on to this one and begin it with x. This is for uniformity. So this one will be plus. Now, you have used this trick before. I can just bring the x first and the s0 to follow. X minus s0. Because I've done that, I have to reverse these two also. So s1 will come first, followed by s0. So x1 minus s0. I've already explained this. It's not difficult at all. So we have p1 of x being equal to this. Now, you see, this is x minus x1 over s0 minus x1 times y0. And then s minus s0 over x1 minus s0. So look at it, you can see that in here, this is x. This is 1, x1, x1. Let me write the x1 well. And then this is s0. Isn't it? This is x, s0, s0, s1. Next, m0 of x equal to x minus x1 all over x naught minus x1. And L1 of x be equal to x minus x naught all over x1 minus x naught, isn't it? Now, if you do this, then this p1 of x, this linear polynomial, will now become p1 of x is equal to, you see, in place of the whole of this, you are going to write L naught of x, L naught of x, and then times y naught. Plus, the one you come in the whole of this, you are going to write L1 of x times y1, isn't it? So this will be the linear polynomial that you have been looking for. Generally, you can say that, so generally, you can write this. Generally, you can say that Pn of x is equal to summation I from 0 to n Li of x yi. Now, so let's look at it. You are getting it from here. Look at it. So, if you take P1 of x, if n is 1, then you are saying that it should start from 0 to 1. So you are going to have, look at it, you are going to have, you start from 0, when I is 0, you are going to have L naught of x, y naught. And then when I is equal to 1, you are going to have L1 of x, y1. If it is a polynomial of degree 2, P2 of x, then I am going to have L naught of x, y naught plus L1 of x, y1 plus L2 of x, y2. Right? If it is a polynomial of degree 3, the same thing. Right? So generally, we can write this. And we are able to get this one from this. You have seen what is happening here. And you have to generalize it. Isn't it? Okay. Where Li of x, where Li of x is equal to the product of x minus sj over si minus sj. These are subscripts. J starting from 0, j not equal to I to n. Yes. Isn't it? So let me use this one to explain, the first one to explain. Yes. What you are saying is that if you need, say, if it is a polynomial of degree, I can now clean this side, then clean this side, and then. Now, you actually write it this way, you call this one the Lagrange polynomial. Do you see it? The Lagrange polynomial, this one. You see, the Lagrange begins with L, so Lagrange polynomial, this. And we are saying that generally this is true, and this is also true. Now let me, we have a polynomial of degree 1. Then what you are saying is that, if you are using this one, what you are saying is that P1 of x is equal to L naught of x, y naught, plus L1 of x, y1. What about the L naught? Where L naught of x is equal to, now let's look at the formula. You see, L naught of x, this one is Li of x. If you are looking at the formula, you say you should find the product of this, and then the j should start from 0, but j should not be equal to I. And if you look at this one, you can see that I will always take its value first. If I say L naught, then straight away I is 0. And we are saying that j should not be equal to I. So if we are now saying that j should start from 0, as soon as j sees that I is 0, j cannot take 0. J will start from 1. So L naught of x will be, look at it, x minus j wanted to start from 0, but j has seen that I has taken the 0. Yes, you got L naught, so I is 0. So j you can't take 0. J will take 1, S1, over, look at it, Si, I is 0. So this is S0 minus S1, because this is J. Do you see it? So L0 of S is called X minus X1 over S0 minus S1. Now look at it. This X1, X1, X, S0. And this is exactly what we have here. Now, what about L1 of X? You guys look on it, but I want you to understand. L1 of X. As soon as I say L1 of X, it means that the value of I is 1. If the value of I is 1, then it means that J can start from 0. So we are going to have this X minus X. J wants to start from 0. Yes, J can do that because I did not take 0. So S0 over Si. Don't forget I is 1. So S1 minus S0. I see it? So S minus S0 over S1 minus S0. Look at it. S0, S0. X, X1. So, if it is L0 of X, look at it, L0 of X, this one will be S0 here, X, X1, X1. If it is L1 of X, L1, look at the 1 here, this is 1, X1, S0, S0. This is for a polynomial of degree 1. That is linear polynomial. Now, viewers, if you have a polynomial of degree 2, then, if you are using these formulas, which we have all derived, then you are going to have P2 of X is equal to L0 of X, Y0, plus L1 of X, Y1, plus L2 of X, Y2. Where L0 of X is equal to, look on the board. As soon as you say L0 of X, it means that I is 0. So this one will be X minus X1. J will have to start from 1 because 0 has already been taken by I. All over S0 minus S1. Now viewers, because it is a polynomial of degree 2, you can't stop here. Because when you are given a question, it will be something like this. You can give you X1, S2, S3, and the corresponding Y values. This one you see Y1, Y2, Y3. So this is a number, this is also a number, this is a number. So after doing the substitution, you left with X. If you are leaving it as X, then it cannot be a polynomial of degree 2. So it means that there is a need to bring another one. So times, isn't it? And don't forget that this is a polynomial of degree 2. So it means that the n is even 2. Do you see it? So you have to sum. The j should start from 0 until it gets to 2. Do you see it? Yeah, if it's a polynomial of degree 1, then the j will start from 0 until it gets to 1. Do you see it? And I'm saying that j cannot take a value that I has already taken. Yes. So because it's a polynomial of degree 2, you cannot leave it this way. You have to get another one. So X minus, don't forget, I has taken 0. So it means that J should continue with 2. J took 1, now 2. And then this one will be S0 minus S2. Because when I takes a value, it is fixed throughout. Isn't it? So this is it. And then L1 of X will be L1 of X will be, so X minus S0 all over S1 minus S0, isn't it? Times X minus, you see, I has already taken 1. And the values available are 0, 1, 2. Do you see it? So J has used 0, then it that J can now use 2. So S2 all over S1 minus S2. Isn't it? Yes, because the first one, if you look at the first one, the values available are 0, 1, 2. Because the polynomial of degree 2, the n is 2. I took 0, so the J took 1 here and took 2 here. Here, I has taken 1. So J has taken 0 here and 2 here. Now let's move on to L2 of S. The last one, as far as this is concerned, polynomial degree 2 is concerned. Now, if you say L2 of S, straight away, I is 2. If I is 2, and the values which were available were 0, 1, 2, and 2 has been taken, it means that the values left are 0 and 1. So J will take 0 first. So that will be S minus S naught all over S2 minus S naught. Don't forget the I is fixed. If it is 2, it is 2 out. Times S minus S1 all over S2 minus S1. Are you seeing it? So look at it. L2, S2, X, S0, S0. The same S2, X, S1, S1. Are you seeing it? L0, S0, S1, S1. L0, S0, X, S2, S2. So it follows a pattern. So this same pattern can be used. Yes, we can just study the pattern, and then if it's a polynomial degree 3, you do it. It's not God at all. Yes, viewers, I've introduced you to Lagrange Polynomial Interpolation. In my next video, you pick a question and solve it using the formulas that we have derived. Okay, thank you very much for your attention. For more of this video, subscribe to my YouTube channel, Shamalaa Jnr, if you have not done so. Thank you very much.